Welcome to the seventh part of this lecture series. So today we'll be talking about the d-separation theorem, as well as go up to hopefully the do calculus as well as counterfactuals. Over to you, Karthikeyan.
Yeah, can you hear me? There's no echo, right? Okay, so I left the previous lecture under some confusion. So let me restate the theorem so that we can go back to that example and clarify it. So actually the theorem is even simpler. So let's first recap. So we looked at some properties like locality, ordering, these properties that any causal model should hold. So we define what is called a CBN. This basically couples a graph to a set of interventional distributions, right? And the interventional distributions are defined using a truncated factorization. Bayesian network is always coupled with respect to only one distribution, and I have not proved it today. I'll prove all of these, some of these claims at least. That the local, so if you have local Markov property that basically connects P and G, then we said this implies what is called d-separation. And this implies that d-separation implies conditional independence. Supports AP. This implication is called the global Markov property. Call it GMP. Okay, this is what we have said so far. And I made one more comment. We'll start off from that. I said that the truncated factorization characterization is actually equivalent to what is called the modularity condition. So there are various ways of stating it. So if you state it in the appropriate way, they are equivalent. So let me actually restate it, right?
What is GMP? Global Markov property.
The global Markov property.
Why do you say global?
Because it says any d-separation implies a conditional independence. So globally, you have these separating sets. They can be very far apart, and you have some subset that separates both. If graphically you can find that, if P was locally Markov with respect to G, it will be globally Markov with respect to P. Not proved it yet. We'll come to it. So this will sort of unravel what d-separation is, how do you think about it, and how it relates to some very classical results in graphical models, basically. Okay. But before we go there, global Markov. I want to clarify this implication, right? So clarification from the previous lecture. So you have P star and you have the object G. And you want to say that P star is sort of compatible, or it's the causal Bayesian network. So G is a causal Bayesian network for P star, or P star is compatible with G if you have the following conditions, right? One is, I said that any interventional distribution, PT of V, is Markov. When I say Markov, it's locally Markov with respect to G. The second condition was the interventional distribution essentially factorizes as the basically the modules which are not intervened remain as is from the observational distribution, right? So here you say that this Vi is not equal to P of Vi given XP, sorry, let's say Xi. That's what I used last time. So Xi, XPFI times indicator that so usually in intervention is fixed to a particular set of variables. So you want T to be consistent with V. Otherwise, you just write 0. Okay. Now there was another question. Why can't I just leave it at this? Why do I need this Markov condition? That was the question you were asked. So a priori, this is just saying what a joint distribution looks like, right? But this actually says the interventional distribution factorizes. So essentially what I'm saying is here PT of B factorizes as PT of xi given xpa of I, like I runs from 1 to B. This is what this statement is. And I haven't told you what PTs are, but whatever they are, it always factorizes this way. Then we are basically saying a specific, if you set it to T equals B, then I can write it as 0 for some of the realizations and non-zero for some of the realizations. And the non-zero number is related to some modules that are there in the observational distribution. So it's not a priori obvious immediately that this implies that. Okay. So they are generally stated as 2 different. Just wanted to be very clear about it.
Can you say more clearly, not clear, what is like 1?
Yeah, because the thing is, there's a support which is 0. Then there's another support where the probabilities actually may not sum to 1, right? In general speaking. So you want to be very careful about it.
They are not, they are independent. One is not equivalent to other.
One is not equivalent. But both will actually specify the correct set of distributions. Okay, but here there's a problem. Like last lecture, someone pointed out, you can have graphs where there is actually no causal relationship between some ancestor and a variable, but you can put a fake edge and call it a new set of patterns. So there are many G's that could satisfy the same P star. Okay, so we have to be very careful when we actually do implications in the sense that it is equal to some other definition. That's what I claimed, right? So what is the other definition? This is actually equivalent to the modularity condition where one holds as is PT of V is locally Markov with respect to G. This is always true. Okay, I'm going to simplify the modularity condition. Turns out that you really don't need for all interventions. You only need to compare the observational and some interventional data. Okay, so what I'm trying to say is P null of xi given xpa of I is equal to PT of xi given xpa of I. Then make sure that xi is not in the interventional set, plus the whole thing is consistent with respect to the intervention T is equal to T. Okay, so the thing is, I just want to check this conditional distribution. I take only the observational one, and I take any arbitrary intervention. I go to the conditional one. Make sure this variable is not intervened. Okay, and I just check these two, and they have to be equal, and that's the claim. Okay, now my claim is that if I can do this for all I, this is called the modularity condition. This is like a conditional independence test, but between observational data and an interventional data. I don't think you lose any generality by adding an arbitrary other interventional distribution on the right, but this is sufficient. It's a minimal statement that you get.
No, consistent with respect to people. Why do you need that?
No, because this conditional distribution could actually be tested for all different xi. Suppose the T was intervening one of the parents. It is setting some of the parents to a very specific value. So it doesn't make sense to compare it with some other conditional distribution. So we just want to make sure that this entire sequence is consistent with T is equal to T. We are only saying I only want equality in these cases. That's what I'm trying to say. Other cases, their equality or not, we are not making any statement. It doesn't make sense to even talk about it because the right answer is not defined, right? Because if it is not 0, it will be 0. Okay. So this is the only set of conditions I'm checking in variance, right? Yes.
Sorry, if it's something I've already clarified. Between 1 and 2 on the first part of the statement, is it not always true? Like where does the so PT of V is sorry above yeah 1 and 2. So is that not product over just the sets not in T?
It is product over variables not in P. Yes.
Correct. What is the first one?
No, this is the distribution itself is locally Markov with respect to G. It factorizes like this.
For only things that are not in T.
No, this is for all V. I mean, this is a full factorization.
For the other elements, it's either 1 or 0.
I have not said anything about that.
Yeah.
But they factorize. So on this concept.
With the parents being.
I mean, that thing is indicator function. It's one. That's it.
So there are these hard interventions and soft interventions. So this the second definition is a hard intervention. Right?
Yes.
You are setting it to a particular value. You should think of the non-variables as either being exactly 1 or 0, something like that, and that is locally marked.
Okay. Now, these two are equivalent. Here also, you can change the graph to anything slightly denser, and you might still make it work, and that's totally fine. Okay, as long as you know what P you're talking about. So here the good thing about this is that in both definitions, the observational P sort of playing an important role. So this is how causal Bayesian networks are defined. So this is called the modularity condition. And I used a different notation last lecture. In the local characterization of Bayesian networks, they capture this by the following independence-like notation. You can use it if you want. So it just simply says that xi is independent of T conditioned on PA of I with a P star around it. This is very misleading. It's basically saying this is independent of some subset of variables. There's no randomness here. Okay, all this says is just the statement. But I'm notationally calling it this because it was used in one of Paul's earliest work, right? So this is basically called the invariance condition. We will see that when we derive rules of blue calculus, we'll actually see that in an appropriate way, this can be written as a conditional independence statement by introducing some extra variables into the system, but we'll come to that later. Okay. This is just a notation. It might be confusing. If you don't like it, this is the thing. Conditionals are the same with respect to observation. And these two are equivalent. For any G, if this holds, it will hold. For any G, if this holds, this holds. It's very easy to prove. But basically, what you start with the locally Markov condition. So you write out everything, right? And then you use the fact that you have intervened in T equals T. So you set all of them to be indicators. Then what you basically do is you look at the remaining ones and you just use this observational equivalence, and then you get back P, and that's literally the second form. Right?
What is the definition of
the interventional distributions? Okay, so that's a good question.
Because the second definition is very general. You are allowing for various kinds of intervention, but the first one, forcing yourself for hard intervention.
Is to say PT of P only probability of P is equal to T consistent with B is equal to 1. Basically, under this distribution, you will see no sample which is not consistent with the interventional distribution. This is my definition. How you physically do it is not very important. All that matters is I get an interventional distribution that's locally Markov. I satisfy the consistency criterion because I look at the column of T. I should only get small t, nothing else with probability 1. Then this should be also true. The moment these three things are true, it's equivalent to the factor. It's a pretty obvious statement at this point. The reverse is actually the more non-trivial one. So the factorization implies modularity, but that you can, you have to work out a lot of factorizations and all that, but it's very intuitive because this factor will always survive, essentially when it's not intervened. So those factors will still remain. So that's not very surprising.
How did you define intervention?
No, I only defined in one of the definitions. I only defined this. This is directly the two distribution. This is descriptive. If you don't like description, no problem. Markovity, consistency, and dimensionality. So by definition, in some sense, modularity is a very powerful signature of causality. And hopefully in future lecture, I hope I'm planning, I don't know if I'll get to that, I'll show you a discovery algorithm that predicates itself on exactly checking this. Arson and others, you can take a look. It started off this whole field of invariant prediction and all that, a proper way. Although the first set of results was, so all that I said is in this paper, local characterization of Bayesian. Okay.
So what was the invariance condition?
This is the invariance. For any interventional set which does not disturb xi, the conditional distribution should remain the same. Only those conditional distributions.
Okay. But now, invariance condition does not uniquely define the graph. If you said any denser graph is still also fine,
Yeah,
right?
yeah.
So you cannot uniquely.
But I think if you impose minimal, I mean, this is my statement. There's no formal proof as far as I have seen. If you impose minimality here, I believe there is some minimality here. But we have not proposed any minimality here. We've just committed to this factorization.
Right. Now coming back to the result you had on linear SCM.
Yes.
You said you will check invariance stuff, which will help you figure out.
No, but if it holds in so many samples, then it will hold. Right. So if it has to hold in so many samples, then it has to already have some sort of minimality. I'm not like committing to like any definition. Just from the data, this is the invariance I found, and it is settled. Yes.
So both of these definitions are consistent with hard intervention. Can they be appropriately
Yes,
explained?
the whole thing is soft interventions.
The only thing that changes is that indicator function goes into a probability.
Yes, there will be an important sampling.
Right. And similarly,
Similarly here. I mean, this statement will remain as it is. You have to be a bit careful about what you mean by consistency. That is the only thing. But if you observably continuous respect to each other, then you can write a similar statement. But it is true that you can generalize a lot of these things appropriately. But it just requires a bit more notation. I'll come to that when I'm doing calculus.
What changed from last lecture is that earlier we were guessing that the graph G was unique, but now we are.
Statement about graph being unique or minimal or anything of the sort. If this is the causal explanation for P star, this will be the modular explanation for P star. That's all I'm saying. Okay. Just want to clarify. Now let me go and prove this one. This is that, okay. This is basically a Bayesian network proof, but I do think it is the correct starting point for do calculus. Okay, it's not very obvious, but so
Those distributions are defined to be.
yes, those distributions. Here it's implicitly defined. I'm not explicitly saying anything because I'm only defining module after module. Then you realize that you just write down what PT of B looks like from just these three properties, you will immediately get the truncated factor. Because the first condition is the same.
But if the distribution is stochastic, it does not do operation.
It is not do operation, but all these can be generalized. It's not so
Do means hard.
That's how the theory is defined. It's the cleanest way of defining it. So I'm just defining that. But you can define using soft interventions and you can still do the same thing. Nothing much will change. Instead of thinking about what happens here, it's useful to think about this property. This will always hold. If you don't disturb this xi using a soft intervention, this module will remain the same. That's always true. Okay. Okay, so before we go to D-separation, so I said something about colliders and so on. So let me give you an alternate definition. Maybe at the end of it, I'll prove it, or it's just a neat graph theory exercise to prove A is equal to B. Now I'll just take the other alternate definition, is much more intuitive, which also answers your complexity questions in a very direct way. Then I'll prove that that implies conditional, because that's much easier. So let me do that. Okay, and you will find that this alternate characterization does most of the job. Okay, so I'll probably prove that later, but it's just a pure graph theory exercise. There's really nothing other than that. The rest of the proof is very beautiful. Okay. So the paper, okay, I think you are confused, so I should be in one place, right? Yes. So let me write it. Okay, so clarification aside, so now today we'll prove that suppose there is a graph, suppose P is locally Markov with respect to G. Okay, so when I say locally Markov with respect to G, it means two things. So I have to be a bit more precise over here. Let me just say locally factorizes with respect to G. By which what I mean is P can be nothing but, P is nothing but the product over the modules. But there's nothing causal here. Suspect it locally factorizes with respect to G. There may be a completely different G, right? And that could also satisfy this factorization. We have not come to any of that. This is just Bayes net theory. No causality. So causality happens only when P star enters, or at least you're talking about one other interventional distribution, right? If you have not talking about anything, just some distribution P that locally factors with respect to G, so it has this form. So that's all I care about. Now P is locally Markov with respect to G means that Xi is independent of the non-descendants that excludes the parent. I'm being very careful here. Conditioned on the parent, so that I don't leave any constants over there, right? So this is locally Markov. It's obvious. We'll come to that. Sorry. The third one is P is globally Markov with respect to G. That says the D separation implies conditional dependency. D separation itself is noted by a similar notation with a subscript D in it, which says is a graphical connectivity criterion. This actually implies independence QC. Okay, so let me recall the definition of D separation. I think we need to go via D connection, right? So a path P connects A and B given Z. If I have to make sure if the path is to be fully talking, no non-collider should be in Z.
Sorry, I didn't follow the previous. P is globally Markov with respect to G.
Yes. If any D separation statement in G implies a probabilistic conditional dependence. This is all in the distribution. This is the pattern.
So for all sets, a Z subset of.
Yeah. So okay. So X, so X, Y, Z are disjoint. And X is a subset of V, Y is a subset of V. I'll prove even with sets directly. Actually, much easier to treat them.
Local Markov implies global Markov.
That's the proof I'm going to. I've not said anything about it yet, but yeah, all three are actually equivalent. If, okay, let's be very careful. So I'm actually looking at Lauritsen et al. 1990. Very classical paper. Okay, it's about independencies of directed Markov networks. So I'm just literally going to just give you what the ideas in that paper are for the rest of the lecture almost. In there, they actually consider continuous distributions, and they just want to make sure they're absolutely continuous with respect to some base measure. It has a density function. If you are only used to discrete random variables, think about the counting measure or a finite support. Anything is absolutely continuous with respect to that, right? So it'll work for all such.
Just okay. So if G is dense, and if X and Y are deseparated in G, they will be deseparated in any sparsor graph.
Correct.
Any subgraph of G.
Perfect.
Now,
Means the conditional equation.
whether there are colliders, whatever.
No. The G separation already handles all possible parameters you might have in your proposed graph. If you are claimed that your P factorizes according to G, these implications will follow. When I haven't proved this link, this is the link I seek to prove. Proof missing. That's what I want to prove. But if you take the proof to be granted, which is true, then you're right. That if you have a denser graph and you already identified independency, if you remove it, that independency will remain the same.
But if you remove the collider, like the denser graph could have a collider.
Yeah, no problem. It's okay. Adding, removing edges will maintain independencies, which from the structure. Or the other way to put is, if something is dependent, by adding an edge, you cannot make it independent. That is always true. Yeah. It is true that you can break colliders and still doesn't matter. I'll show you what, yeah.
Does first imply second? I feel like it's almost marginal.
Yes, I think it doesn't come, but it just needs a. Yes.
You can't go upward.
Yeah, we'll prove all of them are equivalent. By the way, there is an analogous set of statements for undirected graphs. Okay, their factorization, I'll come to that. Actually, the whole thing goes through undirected graph anyway. There, these three things are not equivalent. The counterexample. Okay, we will go to that, but there are counterexamples. Only for directed graph they are equivalent as long as you have a density function. So you cannot have a continuous function with some Dirac delta mass in one particular point. Then these things will go for a toss. Okay, that is the only thing. But otherwise, as long as you have continuous densities, you are totally fine with respect to a base measure. Yes.
So I'm not following what these maybe yeah.
Because the statements are here, right? This is a factorization. This is a specific set of independent statements, one each relating the parent and the non-descendants with respect to a variable. This is any deseparation statement implies a lot more conditional independence. There are exponentially more conditional independencies over here. I'm just merely saying that these statements are true, but I want to prove that the second implies the third. These are just definitions.
Yeah. So second, the third statement itself looks like a proposition or lemma. Like no.
If this holds, if for every deseparation statement, if you have a conditional independence, then P is globally Markov with respect to G. Okay, I have not told you that it is.
The third statement simply defines deseparation.
Yes, it's a it's a definition of global Markov. Deseparation is a separate definition. The implication between two properties. See, the definition relates two things. I have to tell you what the relation means. Relation means the following. If something combinatorial holds, then something probabilistic will hold. That's all it says. But it just says that for a lot of connectivity, whatever patterns, it implies a certain signature in probability. So quite a lot of statements.
Yeah.
For all deseparation.
So so if I was to make this statement for all deseparation, the right side is implied, the probabilistic statements are implied.
If you can check that for a P and a G, then P is globally Markov with respect to G.
So there are graphs where
of course, there are graphs and distributions where P is not globally Markov with respect to G. It will be Markov with something else, perhaps. But this is just a definition. Okay. This is another definition. I'm just going to prove that these definitions are equal. Okay. If it has a continuous density. The density part I never get to. I will just hide in front of the rug. But you can go to Lawrence's paper to see where exactly the measure theoretic arguments are. But the rest of them I just put. Okay. Now, this is very difficult to work with because the connection itself is a very complicated thing. So I have to simplify it, and I'll do that now. And then I'll go back to these things and use undirected graph theory. This is much easier. Okay? That's how the proof also goes. So let's look at what is D connection. The path P connects A and B even given Z, because we want to make sure that no non-collider is in Z. Otherwise, the path cannot connect. So no non-collider in P should not belong to Z, the first condition. Right. So the second condition is that for all colliders, either the collider itself is in Z or some descendant is in Z. It's a mouthful, but that's what it is. Yeah. Yes.
Sorry, I'm still trying to observe the previous.
Sure. Take it.
So there are a set of graph theory statements and the probabilistic statements. The number of probabilistic statements you're making are many.
Yes.
Whereas the graph is only one combinatorial object.
No. But I'm taking. So this is deconnection. Now deseparation means no deconnecting path. No deconnecting path between A and B given Z. Right. So this is the definition. This is the definition of deconnection. So for every triplet of variables, I am having a connectivity statement that I have to go to a given graph and check. It's a 1 or 0. If it is true, then something else is also true.
But all of it is captured by the graph.
Yeah, true.
So I'm saying.
But I have to check all implications.
Right, but I'm saying the graph somehow captured all the information on the left. So is it compressing all the probabilistic statements?
Yeah, that is the proof that it is compressing. Because here there are very few statements. Even before that, there's only factorization. I'm saying just when you factorize, it immediately implies so many equivalences or other implications. So when you commit to a factorization, you are committing to so many conditional dependencies. That's all this is saying. It's just signatures all over the place, provided you can test that. This is for all colliders. Just take a path. If it meets, that's called, okay, this is a collider. Yeah. This is non-collider. This is also collider.
What's the difference between collider and unshielded collider?
So unshielded collider is when the end points are disjoint necessarily. In the graph, there is no other edge between those 2 points also. I am not making any such claim. I'm just saying that there's some path. That's all. And it collides or it doesn't collide. Because it's only with respect to a local argument with respect to the path. Okay. Now, because this is very difficult to digest, it's better to move on to a more manageable definition, which is, by the way, by itself is a very beautiful connection. I don't know who showed it first, but it seems to appear first in this paper. So I'm assuming around that time it was realized by a lot of people. And this is the connection. Before we go into Bayesian networks, let's spend some time with conditional independencies, undirected graphs, and so on. So this is undirected graph. It's a different thing, different object. Forget about everything I've said. Just go and introduce new set of things, right? Okay, an undirected graphical model is just there is a okay. There we use G. So maybe undirected one. I don't know. I just use GU. Is that fine? So this is an undirected model. There is no orientation. Okay. So the way it's usually defined is the following. You take a bunch of maximal clicks. In the graph, let's call it C or calligraphic C, right? And you just say the distribution over V factorizes as follows. There you go. Clicks. That's it. Maximal clicks.
They can be intersected.
So you can have, you can have things like this. This could be smaller than this, but then it has some extra stuff, therefore it's maximal. And all these clicks basically take. Actually, you don't need the maximality. You just have a set of clicks. This is the factorization. When you put all those clicks in a graph, whatever graph you get, that is GU. That's much easier to define. But if you don't like that, you can have this definition, basically. Yes.
That is not defined.
Psi is some factor. So what I'm saying is the density function factorizes this way. This is one function, measurable function, over these variables. So I take the product of these things, that will define the density. When integrated, it becomes the one. Okay? This is undirected graph. Okay. Now, with respect to this, unfortunately, there is another separation statement, but this time it's much easier. So I called it d-separation. So I don't want you to confuse with this. So I call like
All
if let's see instead of all. Ising models. So Ising models you have to be very careful in how you write it. You can either take all factors and take all maximal clicks and write them together, and those will basically be forming the maximal clicks, and you can draw the graph. Or you don't have to necessarily commit to any maximal clicks. This is one way of defining it. You can just take a set of all clicks and basically just define a factor. And you can drop some factors also. You can just make some of the factors one. So in that way, you have a lot of flexibility. An Ising model is always defined with respect to an edge as a click. It's not maximal. But you could write a maximal version. But if you don't like it, let's just say you have a set of all clicks C, and you just have a factor for each, and just do a product, right? And in Ising model, you will only take clicks of size 2, and you will put a factor for that. And that will be your inverse temperature. So Ising model is a special case. Yes.
Follow why they should.
definition.
So just a definition.
So you're saying joint probability of all the vertices being equal to B.
No, I'm not saying that. So you just take a set of all clicks, define some functions. If the distribution factorizes in this particular manner, then this is the undirected graph. That's all. Just put all the clicks together, you should get the undirected graph.
It should be B maybe.
Yes.
Why were we able to remove maximum? So you're saying that if I have factorization with respect to maximal click, there's some psi 1. I'll ask some psi 2 where I can now factorize with every click also.
Yeah, because any click has to be a subset of some maximal click. Right. So it's really about what factor you want to choose and all that. I mean, if there is a factor involving the entire maximal click, then it will anyway be the maximal click. So it's equivalent actually. But upon thinking, I thought, okay, I don't want to confuse you guys. Just take all the clicks in the graph. It's quite a lot, but you can just write the factorization. Maybe many of the factors will be 1, but that's okay. Just add 1, 1, 1, 1, and that's okay. Right? And you put all the clicks together in one graph. Right? Or rather, there is a graph, and there are clicks in this graph, and this factorizes according to this. Okay? Yes.
But won't the clicks have any connections?
They have connections together, intersect into all the.
And therefore, would they not have? Would the probabilities not depend on parents?
There's no parents, nothing, no orientation, nothing here. It's just clicks, just undirected.
So this is the definition of undirected graphical.
I'm not saying anything. So P is locally. I mean, I don't hate to say Markov because you start. GU. So okay, but undirected version of Markov with respect to G. Okay. There's a separation result here. Okay, there's also a local Markov result. Also separation result, but I won't go into it necessary. So let's just go to the separation thing here. Here it's very simple. You take you take 3 subsets x, y, z. It's a subset of B and all disjoint. The same stuff. Basically, you just take all parts. So if Z blocks or separates all paths between x and y, then simply x is I don't know if there's an undirected graph here, so I have to be very careful. I'll just use GU is separated by y given z. Right. So you have an so basically, so if you have a component here, you have some one line, and then you have this. If you just remove one variable out of here, z cannot this component cannot talk to this component, right? And therefore x and y are separated given this particular node in this undirected graph. That's what I denoted.
So when x and y are set, it blocks all paths from all vertices in x to all vertices.
All vertices.
Cut set.
It's a cut. Correct. Yes.
So psi of xc might be something of the form p of xc given something.
No. So I haven't told you one more operation, moralization. I'll come to that. Then the relationship will be very clear. You can always derive an undirected model out of a directed model. I haven't told you how to do that. That's why I'm doing all of this. Okay. Now, what's interesting here is that the factorization implies this. We'll prove again, but factorization actually implies this. So actually very simple to solve. Okay.
What do you mean? This is an independent statement.
Yeah. Okay. So yes. So if this implies independence in P, then invent a new notation. P is globally Markov with respect to the undirected, the undirected globally Markov property with respect to GU. Right? So that's the statement. So this is the definition of blocking. It's very simple, normal separators that you're used to in computer science. I know there's a lot of theory on separators and so on. So that's the same separator. And this implies some conditional independence, right? And this is called globally Markov with respect to GU. And the claim simply is that if it factorizes like this, and if it comes from this graph, if the P factorizes according to clicks, then this is immediate. So here already, I mean, the reason I went maximum clicks is that I thought directly I would hint a relationship to causal graphs and all that, but I will not do that. Yeah, because then it just gets complicated. I want to do something else here. Okay, the interesting thing though is that this does not imply factorization. Apparently, there are examples. Unless your distribution is absolutely continuous with respect to a product measure. It's a very specific requirement. Densities being absolutely continuous with respect to Lebesgue measure means it's just continuous. There's no Dirac delta. That's all it means. But being absolutely continuous with respect to a product measure is a stricter requirement. If you have that, then the reverse also holds. Okay. So in some sense, the undirected connection is weak. The directed connection is very strong. Okay, that's the point I want to make. But the implication from factorization always flows downwards to global Markov property. Whether the global Markov property will constrain the factorization or not is the problem. But in directed graphs, no problem. Now you have density function, you're through. Is that clear? The statements I'm making. So here this holds, but reverse is not true.
Even for something that you might not consider as pattern.
Yes.
Which is subnet.
Yeah, but I don't know the example at the top of my head. But there is an example.
But like one has to be called because on the face of it, these global properties, both here and here, look much more strong.
Correct. And the other thing I want to point out is that the reverse being true, I think, is what is called the Hamer-Clifford. I don't remember. It's called the Hitsey theorem in exponential distributions and so on. People often quote this. I think it's the Hamer-Clifford theorem, right? So nice. It's a 74 result that the reverse is true under some conditions. Okay.
Gaussian distributions.
Yes, based on this slide. So that brings me to what is called graphoids. But if I keep introducing one more combinatorial quantity, it will be too confusing. So what I will now do is I just have to like decide what I have to do and so on. I first prove this, just for you guys to see why this is true. Then I use this to actually make a connection to d-separation, which I'm going to talk about. That's the last third combinatorial thing I'm going to use. I'm not a d-separation statement, but it's equivalent to this likely. And then I'll come back. I find it very neat because a bunch of definitions leads you to the proof. But there are other ways of proving that directly using directed graphs, but then you have to just go through parts and all that. I have to confuse you with all sorts of arguments. This I feel is pedagogically also very neat.
Sorry, I'm not still understanding that clique part. In the right hand.
No, forget about that. Forget about that. That's a different distribution. These are different distributions.
Yeah, just one question.
Yes.
So in those, you have the probabilities of the inside terms of the joint distribution had to be, you could factorize given some parent.
Correct.
In psi of xc, there is no parent.
Coming to that. For now, there is nothing. Just clicks. Let me tell you. Yes. IISc is just a factor. It's just a measurable function. Right? You must be able to integrate it. That's all. Okay. So here I'll tell you an interesting example. A, B, T. It's sort of at the heart of that. Look, independency is implied by this. A is independent of B. A is dependent on B given C. And C is dependent on B. C is dependent on A. There's nothing else, right? I mean, condition on A, B, and C are dependent. Condition on B and C are dependent. That's again implied by this. Now, tell me an undirected graphical model that is satisfied of this. You can't. Okay. You have to risk making this dependent at the minimum. You cannot have three variables, but these two are independent. You cannot have an undirected graph. These two are independent. Condition on this, these two become dependent. Right? This type of collider phenomenon cannot be realized in some sort of an undirected graph. That is one of the main reasons why there is a problem. Okay? Just wanted to make that very clear. The only thing you can add is you can give up certain independencies and make them dependent by just doing A, B, and C. The most interesting independency was this. That is lost. But you have to give it up. This is the simplest graph you can actually fit. Okay. So you have a bunch of independencies you want to explain. You couldn't. So now you're trying to look at, okay, can I explain some subset of independencies? That you can using an undirected graph. So just pointing out that it's not like for all distributions you can find the undirected graph and you can write it like this, where you can describe all independencies you would like to describe. In some sense, you want it to be structured. You know this is structural, right? Because you know this comes out like this here. But the point is that you cannot actually describe. That's the main point.
Okay. But when you went to undirected, you want to preserve independency, but here you preserve a subset of it. Like the graph I would have constructed.
No, all I'm saying is that if there is a directed graphical model, there is no undirected graphical model that will imply the same decept. That's the point I'm trying to make.
A scheme set of words. In fact, this is quite hard. Looking at ungraphical analytic graph, conditioning on something dependent, not of. This phenomena in general, like, condition on something it is become dependent.
Yeah, I mean, I can form distribution where it's possible, only that you need directionality for that. So collider bias, you cannot realize from undirected graphical models. And collider bias is the main reason Simpson's paradox is non-trivial. We'll come to that. Okay, that's why you need to go towards Bayesian network. This is another way of, I think Reichenbach's principle and collider bias do two different things. They are two flips of the same coin. And you want to capture that, you need to go to directed graphical models. If you have undirected graphical models, you cannot capture collider bias. I just told you. So that's an intuition of why things are separate. But I want to sort of, use only undirected graphical models and reason about it. Then what do? Right? You can define undirected graphical models over marginal distributions. Okay, there's no one directed graphical model that can fit all the distributions. But if you want to explain only one conditional independency, can you sort of derive model from a subset of variables? Because if you want to check if A is independent of B, you don't need to know what the other variables are. You only need to know the two distributions. That's from basic probability theory, right? So if I want to test that, I only need to know the marginal distribution. So if I can find an undirected graph with only these two variables, where the d-separation holds, I'm still okay. And that's a new concept of d-separation, which is the following. So what you do is, so you form what is called a normalized graph. It's usually said in the following way, but it's probably kosher to say that anymore. So it basically says that if you have unmarried parents, you marry them, remove all the orientations, you get what is called a moralized graph. It's called moralization. So if you don't like the terminology, all it simply says is that if you have unshielded colliders, basically add an edge for path, edge to the path. Drop all orientations. This is called a moralized graph. This is undirected. Okay. And if I do it here, if I all the actually get this. But three of the differences I want. Be careful what I do. So if I want to capture all these separation statements, what's the right thing I have to do using moralization so that you actually realize it as this unconditional deseparation? That's what I will.
So just repeat what you said with these graphs. So for the first directed graph, four of those conditions hold.
Yeah, just look at the independence.
Correct. And for this graph, what holds, what does not hold?
There's no independency.
Right.
Everything is dependent on everything, conditional on everything.
And moralized graph, therefore?
So this is the moralized version of this. But if you're looking, so if you do one moralization on the entire graph, you can't hope to preserve all deseparations. Clearly, here's the counter example. So I need to do something more. And I'll tell you what that something is. This is just moralization of a graph. You take any directed graph and moralize it, this is what it means. You marry the parents, drop the orientation, you get an undirected graph. It's very nice and simple. You would like something to hold in that, but generally it doesn't. So I have to do some more work to basically show by what the separation. In order to prove this here,
So if there are no colliders in my directed graph, then it is basically this statement.
Cool. Correct.
A and B are independent if Z separates them.
Perfect.
There is no.
Why? Because this only one will always hold. Because there are no colliders in the graph. That's what you said.
No. The path could still, there are no unshielded colliders, but the path could still have a collider.
Yeah. This careful.
So the statement.
There are no colliders, there are no descendants of colliders, which is fine. Then just look at p-separation, just means whether they are connected. Any path, and forget orientation. There are no colliders. The second condition, there were for all colliders, you just want there is a path. There is
The head match.
yeah. If there is a path, they are reconnected. There is no path where we separate.
No, but
The path could still have colliders.
There
No,
are
I-
no colliders. The graph means that there are no colliders in the path.
So there are no, I'm sorry, I should have, there are no unshielded colliders in my.
Even if you don't have unshielded colliders, I don't think this will work, but I don't have an example off the top of my mind because it will be Causal and all that. I don't know if separation alone can guarantee this because I'll shortly show you what the equivalence is. You need to take a subgraph and only then argue about the connection between these two. So I'll just go there, then it will become very obvious. Okay, but that's not enough. The short answer is the short.
Immediate hard times for this, but it's the other direction too. Like any, so you have this family of.
No, let me finish this and then you can, because I've not yet told you what would capture all this yet, right? So what sort of undirected separation capture deseparation? Right, that's what we are after. We want to simplify things. Very simple. What you do is, so if X and Y are deseparated, given Z in G, which is directed deseparation, then what you do is you take the ancestral set, the minimal ancestral set of X union Y union Z. Meaning just put all X union Y union Z, look at all their ancestors, right? And just put all of them in. Don't include anything more. Okay, that is called the minimal ancestral set. Now look at G, the ancestors of X union Y union Z, then raise it. Okay, you will get some graph. It is easy to check conditional independency between these three sets, because any property among these sets can be checked only by the joint distribution on these sets. You don't have to worry about this. That's the main intuition. That's all you need to do. Here, actually Z separates X and Y. If and only. Okay. Why is this true here? I'm only asking for marginal independency between A and B. So what's the modernization of A and B? Dropping C? Well, it's very simple, empty graph. N. So a dependency can be produced by colliders, right? So that if they are in the conditioning set, of course you must take all. So what you do is you take the ancestral closure of all of them and just disregard other things, because there could be other things that could go, or the other things that could connect in some very trivial ways. You don't want any of that.
Ancestral closure does not include the nodes.
No, it includes X, Y. It includes ancestors plus yourself.
So then, in this case, with A, B, and C, it will include A, B, and C. So
C is empty here.
Conditional independent statement Z is empty.
Z is empty.
So why do I need to include ancestral? I mean, ancestral empty set is empty.
So including ancestors is very trivial, because any path which goes through one of the descendants of these objects, there should be one collider.
Correct. You want to capture those colliders, but you don't want to go to descendants of colliders and argue about some very weird connections, basically. That's exactly all this is trying to avoid.
So once you go to the descendants of these things, your path will have a collider, because you have to come at some point, but you're not conditioning on it. So there will not be a connection to the descendants.
Exactly. That's the key here.
Let me summarize at least the statement. You want to just think, not the proof, but what is the statement saying? It's saying that deseparation in G is the same as the following. Look at X, Y, and Z. Look at them and their ancestors. That's a graph to modelize. I become undirected. And now just test whether G is a separate.
That's a very simple way of understanding deseparation if you have trouble with that. It's equivalent. Right? I mean, I know that you guys will appreciate it, so that's why I was going through this proof. There's another way too. It's a bit more complicated. You just keep arguing more and more about, oh, there's a collider, there's no collider, then what happens, and so on. Right? So this is an exercise. I'll come to this. I may not have the time to prove it, but if you buy this, which you can prove, it's just a matter of, you have to be very careful though. There are very important subtleties.
So what?
How do you prove? Let me prove one direction, maybe.
Just one. separation statements are preserved for different orientations. There are many different G's which have the same deseparation. Where this normalization, these ancestors are changing across these different orientations. But somehow, yeah, what is that? Is there any nice way to see why this consistency is preserved in the two?
Okay, so think about the case you said. Unshielded colliders are taken out.
Yeah.
Right? So the moralized graph will be the skeleton.
Right. Right.
You do agree that there are multiple orientations for that.
Right.
But the deseparation statements can be read if you take the appropriate graph out of it, depending on which orientation
you take
those
any orientation and now look at this ancestry.
Exactly.
For different orientation, this graph is changing, but somehow it was helping you to read out.
No, in the Markov equivalence class, you have to preserve the skeleton,
Right.
and you have to avoid colliders. So you can the orientation. It has to be an orientation that avoids shielded colliders. For your example, you go to each of those graphs, and you look at each of those deseparation statements, and you look at each of those ancestral graphs in that direction.
But for these model graphs, any click can be made as the start of
Correct.
graph.
You might be able to verify using one ordering. I'm not saying
it is very surprising.
that is very surprising. Yeah. The combinatorial connection is surprising. I don't know how else to interpret it, but it's what it is.
Is there a variable in front of the ancestors? That's a unique set.
See, the problem is, if I have x, y, there is some g. Okay, g is not a descendant of x, but you could define ancestral set to be a set where all ancestors of every node is present. Okay, sure. So if I include all this, still it's present. But I don't need this weird g hanging in there. I don't want such non-descendants. So just delete them. I mean, it depends on what you mean by the ancestral set. I think I probably didn't define it properly. It just means all ancestors of x, y, z are contained, and you want to pick the one that is the minimum. If there's a reason to be included, don't include it. This is an example. For x, if I want to include the ancestral set, I could use x, y, g2 because y, which is an ancestor of x, is included in the set. But I want it to be minimal because I can throw away g and still retain an ancestral property. So just have a minimal ancestor.
That have a path to it.
Directed path to response. Okay, that would be easier definition. I should have said that first. Yes.
So moralization, I have a question on that. So you mentioned what it does to unshielded colliders. What does it do to other edges?
Coming to that. I need to. So let me prove one part then, right? Because I've already crossed through many things, and I want to prove all those steps.
Does this sequence have a name?
If you have a name, it's there in the paper. It's just an alternate characterization. There's really nothing.
This is super nice. Yeah, just look at the ancestors, modelize it. You're back to standard search.
So one more comment I make, right? Finding a Bayesian network in Gaussian graphical models is also a very hard problem. Right? If I have a dense graph, it's not very easy. Okay. At least the most general one. But finding the inverse covariance matrix is trivial. Just take a covariance, you invert it. I mean, we have enough samples will converge, or you do some inverse covariance estimation. It's possible in polynomial time. Right? That is why this moralization, this ancestry conditioning is so important. Because otherwise, you could have just moralized the whole thing, and you will just be reading off all Markov equivalences and causal relationships and deseparation statements. That's not true. You need to take subsets of the moralized graph. You have to moralize it again and again. So you have to take the inverse covariance estimation of the subset of variables. Then you have to take the inverse covariance estimation of the subset of variables. You have to do it several times in order to ascertain any conditional intensity. Right? So even for Gaussian graphical models, this is saying something very non-trivial. This connection also we have used it a little bit, a very clever way. If you have Gaussian graphical models, then you don't need conditional independence. You can just use inverse covariance matrix and test that directly. But you need to first do the marginalization and then moralization. So that's the key I'm trying to say. Okay, now let me first assume this. It's actually a nice graph theory exercise. You can try to prove it, but I'll try to prove it soon. But more importantly, the big picture is I wanted to prove these two connections. That's why I went on defining so many things. So let me assume this and prove all of them and then come back.
You're assuming that this E of AN and the D separation to undirected is equivalent to D separation.
There's no D separation for it's called separation.
Separation for this is equivalent to D separation. That's right.
Yes. Okay. Okay. Now let me quickly move through the proof because otherwise there would not be any point of doing so many things. So let me just erase this complicated definition. We'll just work with the equivalent definition and show you how beautiful the whole thing becomes. Okay.
Completely drafted in
The graph theoretic statement. I'm not doing anything about probability distribution. The combinatorial recharacterization basically proves something very fundamental about distribution. Okay, so that's the interplay. Yes.
So if we have to prove it on our own, like the combinatorial argument, what exactly do we need to prove that? So to prove equivalence, what exactly?
You need to handle colliders. So let me tell you. So if you have A, actually I'll then go proof it there. So if you have B and if you have S, right? Let's say in your ancestral graph, S is not separating A and B. Okay. Now I have to prove that S also does not is deconnecting A and B. Right. So what one could do is you can consider directed paths, and you could consider directed paths like this. Okay. These are trivial cases. Right. They cannot pass through S at all. Because if they ever pass through S, then there is a problem. There is a problem. Right. So this cannot happen. So the path cannot be. So the path that you take cannot be in such a way that there's only one direction in this way or the other way. It has to involve colliders minimally, right? Because if it separates and if it's apart, then it's very trivial. It cannot happen because I said that S does not separate A and B. That basically means there cannot be a path that actually goes. I mean, the path that you are considering cannot actually go like this and not have any collider at all, because in that case you are blocking it. Right? Because I am blocked it, so I'm not allowing them to communicate at all. So this cannot. But saying that will completely avoid everything, well, that is one case. So if there is a doubt, the only thing that can happen is it will avoid S completely. But that's not a very interesting case. I'm more interested in a case where the path intersects S.
So S should separate them in undirected.
Indirected also. This is undirected.
Yeah.
Okay. So now what is a very complicated case? We can in the thing could intersect that. This is cool because now we're opening it. So this is still connected in the thing. But this is a collider. But suppose it is not a collider. But it's a descendant of some collider. Even then it is fine. But now the point really is that the path has actually missed S completely. But the thing is a descendant is actually in S. So this should happen. Okay. There's one more thing that can happen. A collider can completely miss So that's what the other possibility that you can have is because of generalization, what you can have is no collider. Okay. So I take off all the colliers whose descendants are variants. I just keep deleting them, right? You are still claiming now that the S goes through S and it is actually connecting them. So what other possible things that it could actually have? What it could have is that there could be a collider that does not have any descendant on S also, but it's hanging in there. But because it was modularized, there was a connection. This could actually happen. Now what you actually talk about is that because it's a minimal ancestral set, you actually show that this collider has to have, if this has to still open, you show basically that it has to have a descendant in either A or B. I mean, I'm just showing it in A. Now what you do is you find another path where these marriages are avoided and you are going to a pure path. But if at all there's a collider, it will necessarily be in S, or its descendant will necessarily be in S. So you do this induction argument again. So that's how actually it's a bit complicated, but that's what it is. Is it clear or it's not clear? Okay, so all I'm trying to say is if you have a path that S blocks, the blocking points are all colliders, you are done. It's very consistent. And that's the only thing it can actually happen. Otherwise, the thing has to avoid this and it has to go to B. Right? This is the only thing that is possible. Now this also means that it connects A and B because the colliders are open. There are no other things that are in S. Therefore, this is connecting and it's very nice. Okay. The other case is when there is a collider that's hanging out there, but it's not a part of S. It's there in the directed graph, but the edges that are passing through the undirected one, there's a fake edge that was created through marriage. But its collider is not accounted for, meaning it is neither in the set nor its descendant is in the set. Then what will you do? Then you make an argument basically saying that its descendant must have been in A already. Otherwise, this cannot actually happen. Okay. Then what you do is you just like delete the marriage edges and then make it path in the. You remove the collider also here. Therefore, you'll only be left with colliders that are in X or whose descendants are X. So we have a path that can be fake edges and there can be colliders that are missed. Okay. So what you need to do is you need to remove fake edges and you need to make sure you pass it through the true edge in the so you are structural complicated in the issue. The way you do it is you basically argue that there has to be a descendant of this guy. If it's not in S, it has to be there in one of the A's and B's. And therefore you basically remove that path out and you connect through a new path. That's how you do. So that's the intuitive proof. But I can do a more formal proof next class. So the most important thing is what does this all imply for the final theorem, right? So that's more important. So let me actually go there. But it needs very careful handling with colliders. So it's a very nice exercise if you guys can prove. But it's there in Lawrence and scientific. Okay. So now what am I trying to prove here? So theorem 1. We wanted to say that if P factorizes this according to cliques, then this implies that X being X being separated will imply conditional independence. You want to prove this? Okay. Now you have this distribution, it's a factorization. Okay. Now basically divide it into C that basically intersects X. Look at the C's that don't intersect X. It's called CX bar. Very simple. We want to basically say that Y cannot have any non-trivial intersection with any of the cliques here. Why? Because if they are, you cannot block it because it's part of the same clique. So X is part of this clique. If Y is also part of the same clique, it's a clique. So it connects everything. So no matter what separator you use, they are going to be connected. Okay. So Y cannot belong to both of them. It actually belongs to only X bar. That's it. So this implies that Y actually should belong to X bar. Cx bar should only belong to the cliques here. It cannot have a non-trivial intersection. So Y cannot intersect. Y intersection C is equal to null for all C in Cs. That's the argument. Okay. Once you see that, so X is only in this, Y is only in this. Z can exist in both, right? So this can be written as f of x. Okay, so I should. Let's say I used a, b. I call this a. Sorry for the notation of the last minute change because I was about to write something very weird. This is CA. This is CA bar. Just change of notation. Okay. This is B. This is B. So the B variable cannot intersect any click where A is present. That's all I'm trying to say. Okay. So this can be written as f of xa comma xz multiplied by f of xb comma xz. If the density function replaces like this, condition is not present. Okay. So that's how the direct trick is. Okay. Now how am I going to use this?
So you didn't use definition for Z here. Like when you wrote
Your
the
conditioning on it.
I'm conditioning on it. I simply said it has to be in this way. The moment I see simplest structure, it's a very simple observation. In other examples, very dark. See, I'm using the fact that it's a click. Very strongly, I'm using the fact that
that basically the definition of Z, that it was separated by Z. I mean, somehow you use the fact you use the.
no, if it was separating A and B, they cannot have an edge. That's all it. That's the only thing I'm saying. Right. That's all you need. That's why I can write the two parts. I mean, I can't miss Z. In fact, okay, so by the way, this involves other things like X others, but you can condition on X others and you can still show that this implies condition X. Yeah.
Why is the product CA phi of XC, the first product, equal to probability of A given B? Why is it equal?
Why is this equal to this?
No. So, okay, I understand that you get two factors, each of, and you separate out the two variables, hence you're saying that they have to be independent. But
Condition of C.
yeah, why is that product of phi of XC equal to the conditional probability of A given C? Like,
No, I didn't say it's equivalent to condition. I mean, I'm not saying it's a conditional distribution at all. If your density ever has this form, it immediately implies conditional independence. Why? Because you condition on Z, it's a product. So whenever you have a product distribution, it is conditional, it is independent.
This question is how do you take that equality?
This one.
Yeah.
Okay, Z exists in all factors. The only thing I've argued is that A exists in one factor by definition. Because all the clicks intersect A, therefore it will have that. But these are the clicks that don't intersect A, so A is not in them. Now I showed P is exclusively here, not here. So if I write all these, by the way, it's enough to take only marginal distribution over XA, XB, and XC and argue this and will be subclicks basically. So the factorization are not full, so there is no complication over that. That's why it's good to work with clicks. Marginalize them out, what remains is also a click. Okay, so you only look at clicks induced by these things. You look at clicks that intersect A, look at clicks that intersect that don't intersect A. My claim is that B is wholly present here. That's the only argument.
So now let me make a statement.
Yes.
I promise you that A and B are separated by some Z prime. By some Z prime, and Z prime is not equal to Z. Okay?
I will repeat the same argument with
now I'm saying I promise you that. Now I'll do the same proof for Z here. Okay. Somehow in the second step, I'm feeling a bit uncomfortable. So I promise you that A and B are separated from some Z prime. And now, but I don't promise you that A and B are separated from C. Okay, I don't promise you that.
if you are given these things, you only take the marginal distribution induced by XA, B, Z. That's it. See, I need this distribution to form the evidence. Okay. Remember, if there is a dependency, it need not be preserved. The only thing that is preserved is independency. So I can't make any claims about whatever dependency that you have. If you claim it is deseparated, Therefore, I took this distribution. Right? This only has clicks over all these three categories. And look at clicks that intersect A, look at clicks that don't intersect A. Very clean case. Then I argue that if this is ever to hold, B has to be wholly contained in this. That also you agree, right? So this factor has what all variables A and C. This factor has what all variables B and C. Therefore, it's a product factor. Therefore, it's
What is the LHS? That is probability of A or B given.
yeah. So what I'm saying is take the marginal distribution of XA, XB. It will also have complete factorization. You can show that over the subgraph.
So A was what and A is what?
These are subset. A and B are separated given Z. I started with these variables. There are more variables in my system, but I don't care. I only take the marginal version of that. And this will factorize again as clicks over this marginal distribution.
And XA and XB, like these are assignments.
No, this is a subset of the indices. This is the random variable corresponding to that index. So x1 till xb is basically my set of random variables. I denote it as b. B is basically 1, 2, 3, and mod B. A, comma B, comma Z is a subset of B. I'm just denoting the indices.
So clicks that when you wrote it as product over C, it is clicks in this new marginalized.
Marginal distribution.
But you only promised me that A and B are separated in the original graph. That implies that they are separated in the marginalized graph.
Because I was told.
The marginalized graph is just a subgraph.
That's a good thing about undirected. Yes.
Where did you use the fact that we are working with clicks? Can we not just say subsets?
So the original distribution factorized as clicks. Okay. I only take the marginals. Then you can show that it will factorize over clicks over these set of variables, but it will be some other factorization. But we don't have to worry about it. It doesn't matter. Yes.
Why is there proportionality instead of equality?
Yeah, I mean the normalization constant. I can write it. Yeah. So usually people like because you want to sum to one. Don't need it actually. Just
Because like in the original definition,
Ising models, you say something is proportional to the factor. Sum over Hamiltonian does not equal to one. We need the partial function. So they say.
but in the original undirected definition, undirected model, their psi we were considering such that it was normal because we were just taking from.
Yeah, but it's just that there will be one big constant and it will come in the denominator, but that's it. So nothing. Okay, this is the undirected one. So I need to go to the directed one. So once this is very clear and the d-separation thing I showed you is also very clear, then it immediately implies independence. Why is that? Because it's a d-separation in the moralized version. So I can prove that too. So now what you guys do, what you have to do is okay. So now we want to prove that it implies independence in G director, in P. Okay. This is what you want to prove. But what do you have? P actually locally factorizes according to G. This is what I have. I don't have anything else. Okay. Now this is a very trivial statement. So look at the factorization. P of xi given P of y. What was the requirement? The requirement was that you need a factorization over some clicks. Okay. In the Markov graph, so what you okay, you care only about this. like A is D separated from B given basically C, right? So in the original graph, you can create cliques of the following form: I comma PF5. So when you model this, the whole you actually start belonging to the clique of the moralized graph. Okay, now I'm going to say one more thing without the proof. If you moralize the ancestral graph of A, B, and Z, then A comes PA of I for basically still belongs to C on the moralized graph of the ancestral graph. It is just a marginalization theorem. That's all. You can actually prove it. It's not very difficult to prove. You can actually prove it. Okay. So essentially what I'm saying is take the moralized graph. So it really includes ancestral set of A, B, and Z, and you start creating cliques. Then my claim is that this distribution P over the ancestral set of A, B, and Z also factorizes in the following form. Basically, I run from 1 to B, not 1 to B. So this I only belongs to the ancestral set. That's it. But all ancestors are involved. So parents will be involved. No problems. So you will get P of Xi given PF. This can be proven. If you moralize this, it will start creating some cliques in the moralized graph. And the ancestral distribution will also factorize according to some cliques. And the Xi and PA are already cliques in the moralized graph. But that's if there is no connection. Yeah. So this is obvious by definition. PAI will belong to the normalized graphs cliques, but this factorizes according. This is so. This is because if there are some hanging things, we can just delete them out because the rest of them will be factorizations. You just marginalize over. You can actually prove it. It's very easy. Okay, that's a good thing about directed graphs. Okay, now I come here. So the next step is very obvious. Right? Because here we said with respect to the ancestral graph, separation and deseparation are identical. And we said deseparation implies conditional independence. So you have a distribution that factorizes according to cliques in the graph. In there, I take 3 disjoint subsets whose union is the whole set, and I say that this is separated, therefore this is done. Okay. So here, this, okay, so just to complete the argument, the previous theorem, structural theorem. So it says that it is deseparated. We know that this is exactly equivalent to A being separated by Z in GU equals G ancestral version of A, B, and Z, and then you moralize them. But we know that the joint distribution is this. Yeah, so I'll just say Xi belongs to this GAN and P of Xi given P of phi. We know this is true. This is like cliques in this graph, in this undirected graph, normalized version of the transistor. Okay. Now, this by the previous theorem that we proved implies that A is XA is independent of B given. I this clique factorization, then further marginalize on A, B, and C to follow through that proof. Just want to remind you that this is one more step which was there in the theorem. Is it clear? So we have a clique factorization. Any marginal version is also a click factorization. Then what you say is separation means that the clicks will be partitioned. You cannot share all the variables that you're looking for in all the clicks. That's the main thing that you're saying. And once you have that, you have conditional independence. And once you have conditional independence, then this is very clear. Okay, this is just so this is okay. The other property you show is that when you have a factorization, the moralized factorization will also have these product of modules. Okay, and that means it's a click factorization with respect to the moralized graph. Therefore, you apply the separation statement of the moralized graph, you get it. I know it's a mouthful, but I think the relationships are very clear. Right? So just to repeat, we wanted to prove that directed deseparation implies conditional independence in P. What do you know? P factorizes according to G. Is the only thing you know, right? Then if I just moralize the entire graph, observe that I, PA becomes a clique. Now I take a subset of them, ancestral set involving A, B, and Z, and moralize them. If I belongs to the ancestral set, then I, PA will belong to the cliques of the moralized graph. Right? That we know. But then you look at the distribution over the ancestral set, because then by just some simple Bayesian net theory, because all ancestors are included, it will also imply product of factorizations. These factorizations click in the moralized graph. Then you go to the theorem. See the deseparation theorem in the moralized graph implies independence. Okay. I mean, I think the steps by themselves are simple. It's really the connection, the structure theorem that is very important. And if you guys want, I'll prove the deseparation equivalence maybe next class. It's just mostly the argument that I showed. It's just a combinatorial thing. But more important is once you have this deseparation plus conditional, there are a million other things that happens in two calculus. That's probably more important. So, is there any questions?
It does seem like even analytically, it seems like an IISc. Yeah.
Actually, there's a lot more story. I have not told you. DAGs and undirected graphs are the simplest way of capturing probabilistic independencies. There's some more story, more interesting story. You can basically characterize independencies when there are latent variables using what are called mixed graphs or ancestral graphs. They actually have edges of three kinds. One is you can't determine the edge, you have bidirected edge, or you have directed edge. It turns out an appropriate generalization of this deseparation using this marginalization and moralization appropriately defined generalizes that. And you can show that whenever that thing holds, there is an independent statement that will hold in your independence. So they are very complicated statements.
So in the latent states, there are three kinds of it. Now, a deseparation statement there is complicated.
Yes, it's a very no. So there is a deseparation statement including normalization and ancestry. Here it's just simply ancestry.
Yeah.
There's something called the anterior set that you have to define suitably. And
The deseparation in this mixed graph is like separation in this new undirected.
new
It
undirected
will still be deseparation and separation.
separation here.
But that will not just include ancestors, but something more.
Something more complicated. Then you argue that whenever that structure holds, there is an independence implied by your whatever model that you have. So there's a more general theorem. If you are very, very interested, again, the same Lauritsen. He has a new book, what's called Graphical Models in R. The book doesn't detail the theorems, but it actually quotes the results. And I have made it computational. There's an R package, you define your mixed graphical model, and you simply ask whether this implies the conditional events and immediately imply it. So you can test all these things very fast. Okay. So that's the thing. And the most general model is what is called a chain graph. It is very, very close to the graph that you will get after you do this, like this collider discovery and all that. what will happen is you'll get chain components. They'll be undirected, they'll be directed, meaning the edges will go only between the chain components. Each of the chain component itself will be undirected. That's apparently the most general graph you can possibly define. I'm just quoting it, but
No, how is chain graph more than taken?
no, with the bidirected edges also. So there can be bidirected edges among the chain components and all that. So that's the most general thing you can define. And there is an analogous deseparation statement, but not ancestry. It uses some other type of sets involving A, B, and C. And you just have a separation statement over there. And the moment you can verify that, you just come to your distribution, it will automatically hold. So it's a very nice, generalization of different sets of mixed graphical models and their probabilistic analogs. But this is for FYI. There are lots of interesting research questions here. You may want to actually read about this. But this is the basic. But the template follows.
This is very nice in the sense you went from undirected to graphical work.
Yeah.
People have done this first.
Oh, yeah. A lot of papers on analyze deseparation, they actually use this characterization. They don't use the other characterization. It's much easier sometimes to think. But you have to keep track of what new edges you're introduced during your normalization. That is the only mental, because they don't appear in the actual graph. So you have to be very careful about that. Other than that, I think this is a very legitimate, this is an alternate characterization. So there is a proof by Pearl using the original deseparation statement. Very complicated, as we can imagine. I like this because it goes through something. People are very familiar with Ising models. You don't need to know causality to know that it's a basic graphical model thing. People know that their separation implies independence if the factorization holds. So all that I stated, the previous theorem at is all classical. There's nothing I'm proving. This is the modernization is the main thing, and this is the key step. Once you modelize and you look at the joint distribution, it literally factorizes according to all the members of the ancestral set, preserving everything because it's all ancestors are included. That's a beautiful property. Yes.
So both in the direct and indirect setting, we proved that deseparation in the graph implies independence in P.
But yes, the reverse I have to prove. So let me prove the reverse.
So what I'm asking is you can't go reverse, so you can't go from the probabilistic statement to deseparation.
No, but I can go here. So I can prove that if independence holds for all deseparation statements, that means with all such normalizations, then I can prove that things is a particle.
But you cannot prove from the independent statements, you cannot prove deseparation.
Yes.
You cannot.
Not deseparation, separation cannot be.
Right, because separation is a stronger statement.
No, there are two things. We have proved one implication implies an. Yes. That's all. You are seeing within the final implication, can the reversal be true? No, that is not true because there are non-faithful distributions. That's the example that I give. Because for that, dependencies must imply structure, but that's not.
So graph is clearly much stronger than just conditional.
What do you mean by that? I mean, subset, you mean? Yes, it captures a subset of independencies for sure. Okay. By the way, you can prove the reverse also, that once you have independence according to deseparation, then it implies factorization. The proof is actually very simple. In that graph, there is always one node that's a sync node. There's no descendants. You do an induction argument that says that for n-1 nodes, the reverse holds. Okay. Then what you do is you just look at the final guy. And what you do is you just condition on everything else. If you condition on everything else, it's equivalent to basically removing one factor. And then the remaining distribution remains. And you show that factorizes according to the thing because of deseparation statements. And that's it. We basically end the game. So it's a very simple.
The statement is that deseparation implies factorization.
So deseparation implies factorization. Yes. So the way you prove, okay, since I said I must, so what we have said is that factorization implies deseparation implying CI. Okay, there's an implication here. We prove the implications. Okay, I want to show that say that for if all implications hold, factorization also holds. The easier way to do it is first prove that this implies local Markov property, which is conditional independence only with respect to parents and this thing. Then you show that if that happens for all nodes, then factorization holds. That argument just involves induction. I'm noting that there is always a thing node. That's all. I think this is something that you can, yeah.
Can I just do this that I'll write the trivial factorization as in sequentially conditional every system. And I'll say that, okay, but this deseparation theorem implies conditional independence. So I'm already conditioning on the parent set. I need not condition on the remaining variables in this distribution.
Yeah, I mean, whatever you are saying is exactly this. Okay, take the joint distribution. Index will take care of this because it will only apply to local properties before in the order. Okay. Then take this alone by again the same local Markov condition. This is nothing but P V sync given parents. P V sync given parents. Why? Because all the remaining variables are non-descendants. This is the sync node, right? So you get this P of the remaining already factorizes, as you have assumed, because it's a graph of size n-1. Proof that. This is the proof. Okay. So basically, we have shown that factorization implies deseparation implies CI, implies local Markov characterization of independent local independencies, again implies factorization. This triumvirate is not true in the undirected model, although we went through undirected model in this case by modelization and subgraph condition. This is one of the very core structure theorems in all of Bayesian networks. From now on, the implications can get quite general.
The sparsity of the undirected graph is sort of, you should temper it by doing this model. So we add these edges.
Correct, you can get denser.
They're quite denser. So it all, and then says that, okay, in this denser graph, it's the separate natural idea of separation.
No, but you have to focus on subgraphs. And depending on which separation statement you want, you have to focus only on that subgraph. And then you have to do the model. So it's not the general density that matters. It's the subgraph densities that matter. That's the problem. You still cannot avoid subset search. For Gaussian models, if I want just the whole normalized graph, it's very trivial. I need to do inverse covariance estimation. And non-zero support will give me the normalized graph, the whole graph. But I can't use that for anything. Why? Because for to test a conditional independence statement, I have to take the ancestors only of those, then normalize that. Right? That means I have to do inverse covariance estimate only for that subset. So I have to do exponential number of inverse covariance estimations. Right? So what was actually a simpler problem became a complicated problem. For Gaussian graphical models, in order to test conditional independencies using separation, very trivial. Just take the inverse covariance matrix. Just look at the non-zero pattern that already will tell you a lot of things. Okay, from data. But you can't do that very easily, even for Gaussian graphical models for causality, because of this subgraph modelization.
It's nice.
Yeah, it's just going to get more complicated. So the next class, which I wanted to finish today, but I don't think I have the time, is that when you do so, the whole theory is saying that if you have a deseparation statement, it implies conditional independence. That's all I've established. Just go back to the DAG word. Forget about everything else. It's just a proof technique. Now I want to relate two distributions, and particularly I want to check for invariances between an interventional distribution and maybe a slight an observational distribution. Let's put it that way. Right? Invariances. What is the structure that would imply this? Conditional independencies are implied by some structures, but what structure would imply this? This is what I understand. It turns out the structure that would actually imply this is again d-separation. This is called an augmented graph. You put the intervention also as a variable, and you create a hierarchical graphical model. You first decide which intervention you are in. Given that, you decide the distribution. You can show that this is a Bayesian network. Not causal, it's a Bayesian network. The moment this is a Bayesian network, you can put the interventional variable into the system. Then you can actually relate two distributions that are interventional and observational in a common framework. The moment you do that, you can actually go between do distributions and non-do distributions. That's what enables treatment effect estimation. And we'll relate back to the original problem of ignorability. So why am I doing all of this? Just to give you a better picture of ignorability. When does that hold? Like if I give you a graph, if I give you a causal Bayesian network, I just look at the graph alone, I don't give you any distribution. Can you tell me when will that potential outcome be independent of treatment given X? When can you say that? For which X can you say that? I can look at these separation statements appropriately and actually make that connection.
You're going to argue that B is P is.
No, it's not that simple. We will come to that. Not so. So you need to go to the do calculus rules. And the do calculus rules essentially at the heart of it relates invariances across distributions in a meta model to d-separation statements to an augmented graph. That's what it does. That's the big picture. And once you have that picture, then you can move between distributions. Once you move between distributions, you can move from interventional distribution to observational distribution or less intervening distributions. You can do step by step and finally come to the observational distribution. There's a theorem that says if you can't use these rules to come back, it's non-unique, meaning the effect is not even unique. So that's a very beautiful theorem. It's the next thing.
But somehow we have to introduce counterfactuals before.
No. This is only interventional distribution. So CBNs are defined only with respect to do distributions. That's the only thing we'll deal with so far. Counterfactuals will come.
Ignorability needs.
Potential outcomes, not counterfactuals. The difference. Is it okay? Yeah.
Where we use the d-separation between the augmented variable and observed variable, right? That's where the d-separation arises of for the treatment effect.
Correct. So what you do is you introduce an augmented variable that indicates an intervention. I will appropriately define all those next time. Then a d-separation statement in this augmented graph will actually imply an invariance condition, saying that under do, some conditional distribution is equal to without the do. That's when you start translating treatment effects to observational. That's a very important, that's one of the seminal results by Pearl. The main observation is that you can augment it, and then you can go to and start relating two distributions that are intervened versions of each other. It might look like a very trivial idea when I actually say it, but it's very powerful.
Sharing some of this, like even the handwritten notes you have, we can paste it with PDFs on the page we are talking.
Yeah, so I will give you the paper directly because I actually didn't write any notes for this class.
Okay.
I just thought you could do it.
Previous notes for papers, right?
Yes, I would. So I plan to write proper notes, but it will take some time. You can give me like few more weeks. About d-separation, about the graphical models, how structure implies independencies, just go to. I mean, I wanted to say one more beautiful thing about graphoid axioms. Unfortunately, I didn't get a chance. So
hoping to answer someone to take scribe, but it's a bit late.
Yeah, I mean, maybe I should have done it before, but if it's not clear on the board, I guess formal notes are.
So just back reference.
That ChatGPT and
No, I hope I gave the ideas reasonably.
I mean, I'm just thinking like 6 months down the line if I have to refer.
Yeah. That I'll definitely make sure. So most of the things were either the estimators I told you were all from all over the place in Hernan's book. I think I need to write notes. But the moment I started with TarNet and XLearner, everything was like a paper by itself. So I can just give you the bunch of papers for the last 3 lectures. So and I need to send you guys more lectures also, more papers also about this conditional independence claim. But actually, this looks so complicated. There's something very beautiful about Shannon's theorems, which I did not say. I should have said that. That's how I should have introduced it. There's something called graphoid axioms. And graphoid axioms come from literally one equality in mutual information, which is, I don't know if you know this chain rule. The information theorists love this rule. So mutual information between X and Y comma Z given W is nothing but mutual information between X and Y given W plus mutual information between X and Z given W comma Y. Okay, it might look very innocent, but what this so this is the most non-trivial inequality, which is used oftentimes in Shannon's theorem. So now what this implies, so you can write the alternate way also. So here what I've done is you want mutual information between a set containing 2 parts conditioned on something. You first take one part and then condition on that part and then look at the remaining. You can do the reverse way also. Okay. Now the interesting statement is if the left hand side is 0, the right hand side is always 0. In fact, if the left hand side is 0, this is 0, and the flip version of that X mutual information of X and Z given W is also 0. That is called the contraction weak union property or decomposition property of mutual information. Similarly, if this is 0, the versions on the right hand side is also 0. That's another property. Now, you know conditional independence of X and Y, Z given W. If that is 0, conditional mutual information of X and Y given W is also 0. Mutual information between X and Z given W is also 0. That's like some sort of a weak union property. So all the properties follow from this one inequality, and turns out the undirected d-separation satisfies all 4. And these are called semi-graphoid axioms. But they are not enough to invert it. But turns out d-separation satisfies 1 more. And they are called graphoid axioms for positive densities. And that's why you can actually go back. Okay, so this is very powerful. This is what enables you to go from one conditional independency to just exponentially many conditional independencies. Yes. Right? At the heart of it is basically going through these graphoid axioms again and again and again and again and again. You can actually prove the d-separation statement. But I avoided all of this and went to only graphs. Okay, so at the heart of it, any conditional independency model will satisfy graphoid axioms. And that's being captured by d-separation. So why even bother with all of this? It's captured by d-separation.
Does it mean that information theorists also could use that?
We have always been using graphs. Who said we are not using graphs? You guys don't see us as using graphs, but we have always been using graphs.